One way to become really accomplished in your field is to get old and just keep doing it for a long time. That's what I... This is actually a return to your group for me. I presented at the '94 meeting in Baltimore. I presented at the San Diego meeting that was soon after that. And it's a real pleasure to be able to talk to you today. I'll tell you, sitting on the podium here, I cannot understand a word that's being said. So I may need to move into the audience later on today, but I think the acoustics are really very poor in this room. Most of my slides will have a key point on there, so if you can read, you'll know what I'm talking about. I'm not going to summarize my own work. What I'd like to do is make this a teaching exercise. Some of you have raised questions about your own personal experience with hearing loss, and what I want to do is to give you some of the basic concepts of what the role of the brain may be in some of the problems that you're having with your hearing. So I'm going to start by concluding. I'm going to give you my take-home message before we even begin, so you'll understand sort of what my perspective here. I want to introduce what to me is a new term. It's a term that I came up with while I was preparing this talk. Other people may have said this to you as well, but this is new for me. And it's the concept of brain deafness. So often in an audience like this, you're really exposed a lot to the notion of ear deafness. But frankly, a lot of the problems that you have with hearing is brain deafness. So when we talk about poor speech comprehension, we had a question on that, problems listening in noise, sounds either too soft or too loud, usually this is a function of changes in the brain, not changes in the ear. So I want you to change your perspective a little bit when you think of your own hearing loss. And I want you to think about brain deafness. Another common condition that's associated with this term of brain deafness is tinnitus. Many of you may not only have hearing loss, you may have tinnitus. So what I'm hoping is when I get to the end of this, you'll have a little bit better appreciation of the role of the brain in these kinds of problems that you're having. So here's my overview. Before I can really get to the clinical implications of problems associated with brain deafness, we have to talk about some basic mechanisms. So be patient. I'm going to keep it at a very general conceptual level, and eventually we'll get to the clinical implications of what I'm talking about. So we're going to talk about how the brain is coding sounds, how sound information is translated into activity in the brain that deciphers what that sound information is. The general principle here is one nerve cell does not do it all. You have to have a lot of nerve cells working together in your brain in order to understand sound. And it's this shared representation that changes with ear deafness, and that's the underlying cause of brain deafness here. We're going to deal with the notion of filters, how individual neurons respond to individual components of sounds, and then we'll talk about why those filters are so important when you're listening in a noisy or reverberant environment like the one that we're in now. So then we'll talk about increased noise sensitivity, loudness recruitment, tinnitus, the problems that I know many of you experience on a daily basis. People with hearing loss don't have problems hearing sound. It's very easy to hear sound. You put in your hearing aid, you turn up the amplification, you can hear sounds just fine. The problem is understanding what those sounds mean. So we don't care in this talk about sound. What we care about is the information that's being communicated by sound. And why do we maintain the ability to hear sound but lose the ability to understand sound? So the sounds that you see in this picture here is a sentence 19th century. Okay, it's just something I pulled off of the internet. So we're just talking about the sound picture that you see here. And what you notice is the syllables that mean 19th century are broken into units of time. So you can kind of look here and you can kind of see 19th century as you look across there. So we have to code the temporal sequence of sound, but most importantly, we have to encode where the information in sound lies with each of those individual components. And you can see the word 9 has a lot of low frequency. This is frequency or pitch. And these brighter areas mean that it's louder at those frequencies. When we get to in terms of 19th, we can see that there's not a lot of low frequency information. There's a lot of high frequency information there. Those are the types of acoustic features the brain needs to be able to encode and then decode for you to understand what's being spoken here. Dr. Lauer has already described a little bit about how neurons communicate with each other, but in general, it's a digital code, just like the code in the computers that you use. The neuron is either in an on state or an off state. Physiologically speaking, it means that the neuron is firing bursts of electrical activity that we call action potentials, or if you're a physiologist, you call them spikes. And they're called spikes because you can see these deflections here where the voltage changes really rapidly, and you have an event that says, in this case, the sound is either on or the sound is off. So you can see this particular neuron generates spikes all the time. It's spontaneously active. But when we turn on a sound, it fires a lot of spikes. And that's what we see these clusters right here. So if the brain somewhere is listening to this neuron and sampling how active it is, it knows that sound is being presented. So this would be sort of relative to the syllables, the timing of sounds. But it doesn't tell us what those sounds mean. And that's what's really most critical here. Amanda showed us a lot of really beautiful anatomy of the brain. The brain is complicated. I'm showing you this, not to explain any of these structures to you, because I don't think you need to know these structures. What I'm telling you is the brain, compared to others, the auditory brain, and compared to other sensory systems, is really complicated. There's a lot of structures in the brain that respond to sound. Within those structures, there are neurons that respond differently to different types of sound. This is a mass computation that's going on here. This computation can change, it can break down. But an important part of this is these computations are also pretty resistant to hearing loss. So you may have a lot of trouble with your hearing aid, with your cochlear implant when you first get it. You start to use it, you get better. Most of you have probably used some sort of an assistive device for a long time. I think most of you would say you communicate better because the brain is getting better at doing these computations and understanding this very artificial signal that's coming out of your cochlear implant or your hearing aid. So let's talk a little bit more specifically about what these dimensions of sound are that the brain has to encode and how those codes exist. So a very simple parameter of sound is how loud is the sound. So what I've done here is I've just created 9 or 10 stimuli. And as we move across stimulus number here, the sounds are getting louder. So a red sound is really quiet. A blue sound or a purple sound is the same sound, but just at a louder level. And we're going to play this sound to neurons in the brain, and we're going to record how do they respond to them. We have spiking activity, and I said lots of spikes means that a sound is being presented. We'll call that discharge rate. So let's look at the first neuron here, this red neuron. What happens when we turn on this red sound? We look at the discharge rate, spike rate. It's very low. It's very low because the sound is so quiet The neuron can't hear this sound, and it doesn't change its discharge rate, so it stays down really low. We make the sound louder. The neuron fires more spikes. We make it louder. More spikes. We get to a certain point, and this neuron is working just as hard as it can. It can't fire any more spikes. So there's a range of sound levels where this neuron is providing us information. Right in here, a change in level produces a change in rate. So if we know the rate of this neuron, we know the level of the sound. That's level coding. Now, do you notice the green neuron responds best to the green stimuli? It's not as sensitive, but it's better at coding louder sounds because it doesn't reach its maximum firing rate at a low level. So we have a distributed representation, a shared representation. Some sounds encode low levels, some sounds middle level, some neurons encode high levels. So think of this as sort of a selective response for each neuron for how loud the sound is. And you need a lot of neurons in order to code that sound. Now let's talk about frequency of these sounds. So this is the sound picture that we looked at before, and I've just broken it into colored bands like I did level. And now we've got neurons that encode low sound, low frequency sounds, low pitch sounds, some that encode middle frequencies, some that encode high frequencies. So to get this entire sound picture, we got to have a lot of neurons, each responding to something different, working together. How do these neurons respond to one dimension of sound and not another? They're tuned. And in particular, in this case, they're tuned in frequency or pitch. They only respond best to certain pitches in these complex speech sounds. Think of this as your piano. If you open up your piano and you look inside your piano, you can see that the keys that make high notes have very different looking strings than the keys that make low notes. They tend to be longer, for the low notes, longer, thicker, fatter, heavier, more massive strings. The cochlea is set up like this as well. If this is a cross-section of the cochlea, I think that this audience has probably seen this cross-section before, but the point is, each of these different regions has a different physical description to it. Some regions are more massive, some are lighter, stiffer, and for those reasons, just like the strings on the piano, they respond differently to frequencies of sound. That gives them a tuning effect that you see here. So a particular location will be very sensitive to this frequency because of its physical dimensions, but won't respond so well as frequencies move away from that. The first level of tuning is determined by just the physical, passive, resonant properties of the inner ear. Amanda described the outer hair cells and how they were related to the coding of sounds. Outer hair cells don't necessarily encode sounds. They respond to the vibrations produced by sounds in the inner ear. And when they do that, they apply energy to those vibrations. This is called an active mechanical process. But you can think of it as an amplifier that allows the outer hair cell to amplify certain frequencies and not other frequencies. So what we've gone from is passive tuning, the gray shape that you see here, to active tuning produced by the outer hair cells. And that's the black shape that you see in those same panels. With this level of tuning, the ability to understand information in a complex speech sound is going to be better because you're responding to less of the total physical properties of that sound. This neuron now is really listening to something very specific. So when this neuron fires, the brain knows that property of sound is available in the speech waveform. There's a third level of tuning that you may not know about because this is part of brain deafness. This occurs in the brain. Neurons transmit information along a chain through all those structures in that complex pathway that I showed you before. Some of these connections are excitatory. They're just passing information from one neuron to another. And that's what I've indicated by the green filter moving up to the black filter here. We haven't really gained anything from that kind of a connection. But there are other neurons in this circuit, and they tend to be responding best to frequencies that are arranged around the original frequency, the green frequency in this case. These neurons do not produce an excitatory response on the target neuron. They actually turn the neuron off. So think about it this way. If you have sound here, at this frequency, the neuron is getting this green excitatory input, and it will respond a lot. If you have sound out here, it's still in the green area, but it's really more strongly located in the red area, the area that turns the response off. So this is going to sharpen the tuning of the neuron, and this is called lateral inhibition. While I was sitting over here, I was seeing some great examples of lateral inhibition because people were having trouble looking at the slides here. And so what they were doing is they were holding the programs up to cover up this really strong signal that's coming out of the spotlights back here. That's really what we're doing with these types of inhibitory connections. We're taking what we listen to, not what we see, and we're focusing it down, again, onto something very specific. The consequences of this inhibitory input are not just on frequency tuning. They affect loudness tuning as well, because even here where it's green, we don't have a pure green input to this neuron. We're out at the edges of these red inputs. So there's a mixture of excitation and inhibition, a turning on and a turning off at the same time here. That will change these rate level relationships that we were talking about before. As the sound gets louder, we'll still produce an increase in the spike activity of the neuron. But as you can see, when we go from green to red here, it comes on slowly and more gradually. So we have filters. I just described the mechanisms of the filters. Let's think of the coding consequences of these filters here. If all sound was just a simple tone, a sound like you get from a tuning fork, we wouldn't really need these types of filters. We've got a broad filter, a medium, and a narrow filter, and I'm presenting a tone that corresponds to the green frequency that we looked at when we looked at the speech waveform a long time ago. This green neuron is going to have an identical response to this tone that's centered right in the middle of its filter. Doesn't matter. It's going to be 100% output under these conditions. But remember, when we were looking at the speech waveform, we had energy in different frequency bands, and we needed to say, are these bands changing over time? So we need to know discrete bands of energy. If we've got our narrow filter and we add two more tones at different frequencies, the red and the blue, this neuron doesn't care. It's fine. It can say, I'm only hearing green. That's good. There's a red neuron somewhere that's only hearing red. And there's a blue neuron that's only hearing blue. I've got the sound pattern. I know what you're saying to me. But look what happens when we go down to these really broad filters here. I can't tell these individual components of speech apart. I hear you speaking to me, but it sounds really muffled. And I'm getting the timing information, but I'm not getting this critical pitch information when I do that. Listening and noise. That's what I'm supposed to be talking about. I finally got there. Listening and noise is really a huge problem. It's a problem for me, and it's the more hearing loss you have, the more problem that you're going to have listening and noise. Noise, you can think of noise as a bunch of tones right next to each other in pitch, all the way across the range of frequency. So these types of stimuli really fill up these auditory filters. If you've got a narrow filter, and this is all your noise frequency across here, you can see there's an area in this filter that's going to have noise in it, and I just call this 1. That's just how much noise is in the filter. This neuron doesn't care if noise is out here because it's not in the filter. We're not hearing that. But here, the noise is in the filter, and it's going to interfere with our ability to hear this tone, the green tone, which is information. That's what we're trying to hear. Look down here. As this filter gets broader, more noise is in the filter. The neuron, listening to this filter, now has almost 4 times as much noise that it has to deal with in order to hear the signal. That's why filter bandwidth is so critical for discrimination of speech, but also listening and noise. So if we turn on noise, energy is in this broad filter. The neuron starts responding. And that's the red rate level function here. The noise is on all the time, and what I'm doing is I'm changing the level of the tone that I want this neuron to encode, to respond to. Remember what this looked like in quiet. That's the green function that you see here. We're expecting discharge rate to gradually increase as we increase the level of the tone. But we can't do that in noise because noise has totally taken over the response of this neuron. The neuron is responding as fast as it can to the noise. We turn on the tone, nothing happens. We don't hear the tone. That's called masking. If we make the filter narrower, we get less noise and we preserve information. We can see we have information now. And the narrower that filter is, the better this neuron is going to respond under noisy conditions. Amanda talked about the olivocochlear system. It's a feedback system that helps you listen in noise. How does this work? I like this chart here. This is a feedback loop. And I think about this when I was working on this talk. I was commuting down to downtown Baltimore in traffic. And what do? You speed up, and then you slow down, and then you speed up, and you slow down. That's the way this system here works. So what we have is the amplifier in the cochlea, which is the outer hair cell, makes the inner hair cell more sensitive. That sends a lot of information up to the brain, and the brain says, wow, I've got too strong a response here. I got to turn things down. So it sends a signal back down to the ear, to the outer hair cell, and it says, change your electrical properties. I want less amplification under these conditions. So when that happens, everything becomes less sensitive. The neuron is less sensitive to noise. That means there's more rate, more information available when I turn the signal back on. So that we go from the response in red to the response in blue. It's bigger. There's more information there. We can encode sounds with that information. That's why brain feedback to the ear is important. Okay, hearing loss. What happens in hearing loss? What tends to be the first thing that goes? It's the outer hair cells, right? I bet everybody in this room knows this, has heard this. I think I just lost a hair cell myself. When, do you hear that sometimes when your ear just rings like that? Yeah, okay. So we've lost outer hair cells, but from what we're talking about today, we haven't lost outer hair cells, we've lost the amplifier. And I've already told you why that amplifier is important. So this is a bad thing. Without the cochlear amplifier, the ear is going to be less sensitive. That's not such a big deal. You can always make sounds louder. It's going to be less tuned, okay, because we're using this feedback to mechanical active feedback to make the filters in the ear better. And we're not going to have feedback anymore. So we've lost three really big things just by losing outer hair cells. And that would be the consequences of the ear deafness in this situation. But there are consequences in terms of brain deafness also, because the brain is always listening to the ear, and it's always expecting a signal, a sound-generated signal from the ear. You start losing your hearing, you start losing that signal. The brain has to respond in an adaptive way to allow you to function better. So what does it do? It turns off inhibition. Inhibition prevents you from hearing sounds. It makes the sounds that you do hear more selective, but you got to hear sounds. So we turn down inhibition. What happens when we turn off these inhibitory inputs to a neuron in the brain? The neurons in the brain become more sensitive to sound. That's good. We want the brain to take up some of the slack here. But we also lose this really critical neural tuning that we've been talking about here. So you're going to have less ability to discriminate sounds when you're listening to speech, and you're going to be more susceptible to noise when you're listening to speech. So these types of changes are not only happening in your ear, they're happening in your brain as well. Now, I hear half of the people in this audience during Amanda's talk were saying, turn up the amplifier, and the other half were saying, turn down the amplifier. This is a big problem. It's loudness recruitment, and it's related to changes of inhibition in your brain. So here is our normal inhibited rate level function that I've already shown you before. What happens when we turn off inhibition? I already said things get a little bit more sensitive, but these functions become steeper when this happens. What does that mean? Change in rate in a normal brain means sounds are getting louder. If the change of rate is coming really fast, what does that mean? It means the sound is getting louder really fast. So you go from a point where you don't hear the sound to, okay, I can hear it. You make it a little bit louder. Instead of getting a gradual change in rate, you get a really steep change in rate, and that sound becomes uncomfortably loud. And this is the neural basis of loudness recruitment. Here's another change. If you look down here, these are the real quiet levels of sound, where you expect your brain to be responding as it would under silent conditions. Very low levels of spontaneous activity. That spontaneous activity is dictated by the inhibitory inputs to neurons in your brain. And we've just turned them off because your ear is getting deaf. What happens to spontaneous activity? It goes up. The brain, the auditory brain, becomes more active, has more neural activity. What does neural activity in an auditory neuron mean? It means a sound is being presented. At least that's what your brain thinks it means. That's what it's usually supposed to mean. But in this case, the increase of activity is just occurring because of changes in these inhibitory projections of the brain, and they're being interpreted as sound. And that's the neurophysiological basis of tinnitus as we understand it now. So let me conclude. In terms of the clinical implications of what I've talked about, we can think about assistive devices. I'm going to preach to the choir and say it's not about amplification. I know you already know that. But it's not about amplification. It's about being able to produce a response that is still selective. It has a broad dynamic range to it, and it's able to discriminate signals from background noise, because that's what your brain is meant to do with that signal here. So the good news is there's a lot of fantastic hearing aid technology, cochlear implant technology being presented at this meeting. It's getting better every year. We have remarkable advances in digital signal processing. Batteries turn out to be a really important thing because it determines how much processing you can do on the sounds. As we learn the real physiological mechanisms for how the brain is processing sounds, we can duplicate these processes, at least in rudimentary form, with better assistive devices. Remember this word. I hope I'm the first one who told it to you. Brain deafness. That's what you need to be thinking about. It's not about ear deafness. The circuits of the brain require activity. When the ear grows quiet, the brain changes, and the consequences of that affect everything that you hear. Finally, what do we do in this case? Someone asked about sound therapy. If activity is important, one thing that we certainly know, you're not going to make things better by not using your hearing aid or not by turning off your cochlear implant. You got to keep getting those signals into the brain, exercising those circuits, and producing more normal types of responses. All right, thank you very much.